Hello everyone, I'm Professor Harrison, and welcome back to our module on matrix algebra for finance. Today we're going to be covering the second half of multivariable optimization. Specifically, we're going to learn how to classify a critical point. We're following Ruth, a PhD student building out her matrix-based methodology for her dissertation. Last time she set up the first order conditions for her two-asset portfolio and solved for a critical point. Today she's figuring out whether that critical point is actually a maximum, a minimum, or a saddle point. She turns back to her dissertation chapter. Last time we set up the optimization problem for a multivariable function. The first order condition was that the gradient, which is the vector of all partial derivatives, must equal 0 at an interior optimum. Setting that gradient equal to 0 gave us a system of equations, and solving that system gave us the candidate points where the optimum could potentially live. For Ruth's portfolio utility function from last time, that candidate point was w1 equals 2 and w2 equals 1. The first order condition by itself only tells us if we have a critical point though. It does not tell us what kind. A critical point could be a local maximum, could be a local minimum, and it could also be a saddle point, which is a point that looks like a maximum across one direction, but looks like a minimum across another. To figure out which one we have, we need to take a look at the second derivative. In single variable calculus, the second derivative test was straightforward. If the second derivative was positive, then the function curved upward, so it was a minimum. If it was negative, however, then that means the function curved downward, so it was a maximum. With multiple variables, the same intuition holds, but the second derivative is not just a single number, it's a matrix. Specifically, we collect every second partial derivative into a matrix which we call the Hessian. For a function of two variables, the Hessian is a 2x2 matrix. The diagonal entries are the pure second partials. The second partial with respect to w1 is in the top left, and the second partial with respect to w2 is in the bottom right. The off-diagonal entries are the mixed partials, which is a partial with respect to w1 and then w2, and it sits in both the off-diagonal slots. One thing worth noting up front, the two mixed partials are always equal for the kinds of smooth functions that we work with. That result is called Young's theorem. Sometimes it's also called Clairaut's theorem, and so the Hessian ends up being symmetric for our purposes. The off-diagonal entries are going to match each other. Let's go back to Ruth's portfolio utility function. The function was 5w1 plus 6w2 minus w1 squared minus 2w2 squared minus w1 w2. We found that the critical point is w1 equals 2 and w2 equals 1. Now we need to compute the second partials. We start from the first partial, which was 5 minus 2w1 minus w2. Take the partial of that with respect to w1 again, and you end up with negative 2. Take the partial of that with respect to w2, and you end up with negative 1. So the top row of the Hessian is negative 2, negative 1. For the bottom row, we start with the partial with respect to w2, which was 6 minus 4w2 minus w1. Take the partial with respect to w1, and you end up with negative 1. Take the partial with respect to w2, and you end up with negative 4. So the bottom row is negative 1, negative 4. The Hessian is the matrix with the negative 2 and the negative 1 in the top row, and then the negative 1 and the negative 4 in the bottom row. Notice that the off-diagonal entries are both negative 1, which is what Young's theorem promised. So how do we use the Hessian to actually classify the critical point? The answer is a matrix property called definiteness. There are 4 possible cases, and each one corresponds to a different type of critical point. If the Hessian is positive definite at the critical point, the function curves upward in every direction. So the critical point is a local minimum. If the Hessian is negative definite, then the function curves downward in every direction, so the critical point is a local maximum. If the Hessian is indefinite, which means it curves up in some directions and down in others, then the critical point is a saddle point, and neither a maximum or minimum. Then finally, if the Hessian is semidefinite, which is the borderline case where there is some direction that is exactly flat, the test is inconclusive at this level, and we would need to move on to more tools to make a decision. At this point in the course, we'll just flag that case. So how do we actually check what case we are in? The cleanest test for our purposes, and the one that we already have the tools for, is to use the determinants, specifically the leading principal minors of the Hessian. The leading principal minors of a matrix are the determinants of the upper left submatrices, growing one row and one column at a time. For a 2x2 matrix, there are 2 leading principal minors. The first one, which we'll call D1, is the upper left entry by itself. The second one, D2, is the determinant of the full 2x2 matrix. The test goes like this. If all the leading principal minors are positive, then the matrix is positive definite. If they alternate in signs starting from negative, so D1 is negative and D2 is positive, then the matrix is negative definite. Anything else and you have either an indefinite or a semidefinite case, which means a saddle point or an inconclusive result. Going back to Ruth's Hessian. The first leading principal minor is the upper left entry by itself, which is negative 2. So D1 equals negative 2, which is negative. The second leading principal minor is the determinant of the full Hessian. From the determinant subunit, the determinant of a 2 by 2 matrix is the product of the diagonal minus the product of the off-diagonal. So D2 equals negative 2 times negative 4 minus negative 1 times negative 1. That works out to 8 minus 1, which is 7. So D2 is positive. D1 is negative and D2 is positive. The signs alternate starting from negative, so the Hessian is negative definite, and the critical point at W1 equals 2 and W2 equals 1 is a local maximum. There is one more thing worth noting before we wrap up. The Hessian for Ruth's utility function has constant entries. The second partials do not depend on the weights. And that means the negative definite condition holds everywhere, not just at a critical point. A function that has a negative definite Hessian everywhere is called globally concave. And for a globally concave function, a local maximum is automatically going to be the global maximum. So Ruth does not have a local optimum here, she has the optimal portfolio, period. Ruth gets up from her desk. She has the second half of the optimization chapter finished. The framework can find a candidate portfolio and certify whether it's actually optimal, not just a stationary point. So that is the second order classification for multivariable optimization. The Hessian is the matrix of second partial derivatives, and it ends up symmetric for the smooth functions that we will work with. To classify a critical point, you check the definiteness of the Hessian using the leading principal minors. If all the minors are positive, the Hessian is positive definite and the critical point is a local minimum. If they alternate starting from negative, the Hessian is negative definite and the critical point is a local maximum. Anything else and it's a saddle point or an inconclusive case. And when the Hessian is definite everywhere, the local result extends to the global one. This type of multivariable optimization is critical for finding optimal portfolios and across the world of finance.